Factorization and counter inference. Hmm. So this was one of the very useful examples that we went through. Like a prime to divide. So I think we gave an example of a prime element which is not irreducible and an irreducible element which is not prime, right? Yes, this was the example. This was a very useful example. But this is very important. So is every prime element irreducible? So P is prime if and only if P is non-zero prime ideal. Okay. C is irreducible if and only if this C is a maximal ideal in any set S of all proper maximal in the set S of all proper principal ideals in R. This is very important result. Hmm. Okay, let's try to prove them. Actually, see, this is, I think, very important. One of the very important things. So, so say one. So P is prime. Okay, and AB belongs to P. Okay, which implies AB equals to PK for some K, which means P divides AB, which means P divides A or P divides B, as P is prime. Thus we have A belongs to this or B belongs to this. Which implies this is prime, right? Conversely, if the converse part is easy actually, you can do it yourself. Look at 2. C is irreducible if and only if C is maximal in the set S of all proper principal ideals in R. So, what is S? S is basically set of all I such that I is ideal in R and I is generated by a single element. Okay. And so if C is irreducible, right? Okay. Now this belongs to S now, because this ideal is generated by C, so this is in S. Okay. So if is not maximal, do you understand what a maximal element in is S is? So an element M is maximal in S if M is not contained in any proper, if M is not contained in any proper ideal in S. Okay. So if C is not maximal, there exists I such that right, which means A divides C, but C is irreducible, which implies A is unit or associate of, this is proper, suppose, of C, which implies, okay. And similarly for the converse part, so you have to see that if something divides this, so if something divides it, so suppose is maximal in R, so if this is maximal in R, and suppose A divides C, then C, this is maximal, right? And suppose this, okay. Now A divides C, so this is contained in this as is maximal, right? So C is irreducible. For third, every prime element in R is irreducible. C, first of all, I would like you to, I would like to take you back to the example. I request you to go through the example again. Please go through it. And and understand why this example works and why this cannot be the case in our proof. Please go through this example once again. You have 2 minutes. Please see it. Okay. So why does this example work? Look at this thing. Z6, right? Z6 is not an integral domain. Okay. And observe the next proof. Okay. See. See here. This is an integral domain. Okay. So when we prove 3 that if every prime element is irreducible in R, so let P be prime so let P be prime in R. So suppose R divides P, which implies uh, P is prime in R. Suppose P divides R. So I will have to show that P is irreducible, right? Okay. Right? By 2. By 2 it is enough to show that this is maximal in F, right? So if then did I write it correctly? Just a minute. P is inside. Oh, P is inside this, so P is equal to this. Sorry. Now P divides P equals to AR, right? Which implies P divides A or P divides R as P is prime. If P divides A, then so if P divides A, you have, which implies, okay, this is a contradiction. And if this happens, that P divides R, then R is some P into K for some K. Put P equals to AR, you get R equals to ARK, right? Take R in common, 1 minus AK equals to 0. Now you see, since this is an integral domain, R is 0 or 1 minus AK is 0, right? But R cannot be 0, right? Because P equals to AR and P is non-zero. So R is non-zero, which means A is AK is 1, which means A is a unit. So this is whole R, okay? Which means this is maximal. Okay. So there we have used the fact that it is not an, it is an integral domain. There we just used the fact. Okay. Now 4. So if R is a principal ideal domain, then P is prime if and only if P is irreducible. This is direct, na? I mean, from 1 to 3, this is direct because in a principal ideal domain, every ideal is of the form S, is in S, right? Every ideal is generated by a single element. So 4 follows from 1, 2, and 3. Every associate of an irreducible element of R is irreducible. Hmm? This is also quite easy. Associate of an irreducible is irreducible. This we have shown that I mean only divisor can be irreducible and unit. These are the only divisors. Okay, so to the next point. Okay. So this is the definition of an integral domain. Huh? An integral domain is a unique factorization domain. Okay, first understand what is a factorization domain. I mean, was the definition of a factorization domain given earlier? Yes. This is a no. Hmm? The definition of factorization domain is not given here. Okay. So this condition one, this is the definition of a factorization domain. Okay. This is the definition of a factorization domain. Every non-zero non-unit element in A can actually be factorized in terms of irreducible. Okay. That it can be written as a product of irreducibles. Clearly, this I mean some of the irreducibles may even repeat. Huh? Some of the irreducibles may even repeat. Hmm. Every non-zero non-unit element A of R can be written in this way. Huh? If and the next condition actually talks. I mean, makes sure ensures the uniqueness. The next condition is if there are two such factorizations, then m equals to n and di and cj. These basically says these are nothing but permutations of this. Okay, I mean it's like I mean let's give you an example. So suppose a is c1 c2 and this is d1 d2. Okay, so they are saying that either c1 is associated with d1 or d2 and c2 is associated with d1 and d2. Okay, so that's that's the meaning of this line. Now, every irreducible element in a unique factorization domain in a UFD becomes prime, right? Every irreducible element in a UFD becomes a prime element. Because, say, if every irreducible element in any UFD is necessarily prime. So, if A is suppose an irreducible element, okay, then suppose A is irreducible, huh? And you divide, I will suppose A divides BC. So BC is AK, right? So BC is AK. Oh. Yes, but since this is irreducible, so you can write like K has one of such decompositions. So you can write this as K1 through Kn. So you see, you look at this thing. So A has to divide one of B or C, right? Is it clear to you? Is it clear to you that A has to divide any of B or C? Because C, A is irreducible, so A can't divide like some factors of B and some factors of C. So if BC is AK and A is reducible, and basically you have to break it up. Suppose B has a factorization B1 to Bm and C has a factorization C1 to Cn. Okay, and this side is AK1 to say Kr. Now you have seen from this that A has to be associated with some of the Ci's or Bj's. Okay, so A divides C or B accordingly. Okay. 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 So for the next point, you like an integral domain R is a UFD provided that no sorry, if R is a principal ideal ring, then and this is a chain of ideals in R, then for some positive integers, okay, so this is called the Noetherian conditions. Okay, okay. I will give you guys 5 minutes to look at this proof. You have just 5 minutes. Look at this proof. Okay, so every principal ideal ring is a unique factorization domain. Like every PID is a UFD. Why? Because every PID is a UFD. Why? Because in a PID, prime and irreducible are equal. We have seen, na? Prime and irreducible, they are equal in a PID, right? Hence, R is a UFD. Okay. No, not actually. I mean, once you show, but you first have to show that there exists a factorization actually. Once there exists a factorization, then it is obvious that it has to be unique. Yeah, that's true. But to prove the factorization, prove a factorization, you will have to use that lemma before. Okay. Oh, see one thing. I was discussing something I mean a few of you that I have actually invited one of ISI's researchers to come and actually conduct the algebra class. He is a commutative algebraist actually. So this is actually his domain. Like I am doing my research in algebraic geometry. So sort of geometry is my domain. So this is actually his domain. So since this is the batch dedicated to M.Math, he will be taking this class. I mean this abstract algebra class from the next week. So he's a brilliant teacher and he was actually my teacher. So I was trained by him. So don't worry, he is just outstanding. So today just he was a bit busy, so he told me that okay, you just manage today's class. From the next class I'm going to take over. So he will start things in a whole different approach. He has his own notes. Yes, he will of course give you assignments from a particular book, probably from Hungerford. And wait a minute, he actually wrote something. Let me see what books he will follow. He wrote something. He will follow Hungerford and Artin, okay? But he has his own notes for theory, and he is just brilliant. So, so I will be taking probably the analysis portion, and he will be teaching the algebra portion because in that way we can increase the number of classes actually. And I'm also thinking about like having separate batches for jam net and M.Math because I do those who are here, yeah, you all of you are M.Math aspirants. So because I believe M.Math and the other PhD entrances like ISI TIFR, these require a little bit more serious preparation than net or jam. These are MCQ based exam and you can actually sort of hit and trial. So these are not very tricky exams. Not mathematically very tricky, but the concept needs to be very sound if you want to crack those ISIs and TIFRs and IISERs. So I thought I need this one of these experts. Another good thing which he will bring is his contacts. Okay. he has actually contacts all over India. So suppose in future, maybe in 2 3 4 years time, you want a recommendation, maybe to go out, to continue an MS, maybe pursue an MS outside India, or maybe a PhD outside India, or maybe you just want to, suppose you have a net or NBHM and you want to go into some of the IITs or IISERs. What he can do actually, not, of course, he can't recommend each and every one of you, but if you are one of the brightest students of the class, he can actually recommend you to one of his fellow researchers. So I think it's a brilliant opportunity, and also he was available. So I thought, why not just have him in the academy. So this is the last algebra class that I am taking. For the M.Math class, he will be taking the rest of them, at least for this session. And I will conduct the analysis class probably. Okay. But again, if you have any sort of doubts, reach out to me. Okay. Reach out to me. If you have any doubts, reach out to me. So this was like ED or PID. We have shown that PID, principal ideal domain, is basically UFD, unique factorization domain. So PID is UFD. Okay. But we will soon define a structure which is called Euclidean domain, ED, and we will show that ED implies PID implies UFD. So what is an ED? ED is an Euclidean domain. Why an integral? What does it mean to be an integral domain? This is the definition. Okay, please go through it. Go through the definition, please. So phi is basically sort of an evaluation map. Huh. Phi is from r minus 0 to the natural number. Okay. Such that if a and b belongs to r, such that ab not equal to 0, then phi a less than equals to phi b. Okay. And for every element a and b in r, b not equal to 0, there is this division algorithm. Like you can take a as the dividend, b as the divisor, and have a equals to qb plus r. If r is 0, and with r is 0 or r less than 0, and we will have that phi r is less than phi b. Okay. A Euclidean ring is an integral domain. It's called a Euclidean domain. A Euclidean ring which is an integral domain is called an Euclidean domain. Okay. So, so there it is. Z is an integral domain. Okay. Z is a Euclidean domain where phi x is mod x. Okay. So phi, the map from z minus 0 to natural number, is basically the absolute value of that number. Okay. Any field f is an integral domain with this evaluation map. Okay. Not actually evaluation map. This is actually called the valuation map. Sorry. This is the valuation map. Okay. Where you are assigning 1 to every non-zero element and 0 to, I mean, every non-zero element you are assigning 1. Margot. So yeah, another example is fx. Like f is a field and fx is a polynomial ring in f. Okay. Now you define the valuation map phi to be, suppose f is a polynomial in fx. Okay. So phi f is what? It is degree f. Okay. This ring is called the ring of Gaussian integers, Zi. Okay. This is of the form a plus bi, where a and b belongs to z. This is also an integral domain. This is also an integral domain. But soon we will show that, like z3i, I mean, suppose elements of this form, like zb root 3i. This is called z root 3i. Soon you will see that these are not integral domains. I mean, these are not Euclidean domains. Some of them are not even Euclidean. Some of them are not even UFDs. So the valuation map here is a square plus b square. Okay. Every Euclidean domain is a principal ideal domain. Okay. So I think so. Let's prove that every so every Euclidean domain is a principal ideal domain. Okay. So let I subset of R is an ideal. Okay. An ideal. So we will have to show that I is generated by a single element. So define sigma to be phi R for R belongs to I. Okay. You have that map. Don't forget it. Since it is an Euclidean domain, you have that map. Okay. Now this is a subset of natural number. So sigma has a least element by Boyle ordering principle. By Boyle ordering principle, right? So suppose phi r naught is the least element in sigma. So our claim is I is basically generated by this R naught. Okay. This is obvious. By the definition of sigma, R naught is an I. Huh? So now if x belongs to I, remember R is an Euclidean domain. So you can write x equals to q R naught plus R, right? With R equals to 0 or phi R less than 0, phi R less than phi R naught. Done. Okay. So x minus q R naught equals to R belongs to I, right? Because this is in I and x is in I. So difference is in I. So if phi R is less than phi R naught, then we observe what? And R belongs to I, we observe what? Phi R naught cannot be the least element. Least element in sigma, as phi R belongs to sigma, right? Which is a contradiction. So R equals to 0. And R equals to 0 implies x equals to q R naught, which means x belongs to R naught. Okay. Which means I equals to R. So any Euclidean domain is basically a principal ideal domain. Okay. So let's define GCD and relatively prime elements. Okay. So I would request you guys to go through the definition. That this is the definition of a GCD. Please go through it. Please. Wow. Ah, okay. So another thing which is very important is that this GCD, okay, this GCD, yes, yes, this theorem, this is very important. So if D is the greatest common divisor, okay, so D is the greatest common divisor. Let's see. So this is an ideal, right? this some ideal, and we know that this is generated by some element, say D. Okay. We will show that this D is a this D is the DCD. Okay. So this is an ideal, and since this is a PID, this is generated by a single element. We will show that this D is a PID. Okay. So since because of this equality, D can be written as A1 R1 plus A2 R2. Okay. So if X divides AI for all I, this implies X divides the RHS, which implies X divides D. So this is the first condition, that if wait a minute, no, if X divides D, no, sorry. The first condition is that D divides each of the AIs. Okay. So this implies summation AI is a subset of D for all I, right? This implies D divides AI for all I. Okay. So this is the condition 1. The next condition is if X divides AI for all I, X has to divide D. So if X divides AI for all I, X divides, so I mean from this equality, from this line we can say that this is A1, right? As D is in this. So if X divides AI for all I, X divides RHS, X divides D. Okay. So D is the GCD. So we didn't directly show that GCD is of this form. We actually showed that the generator is basically the GCD. Okay. The proof is same for this. If R is a unique factorization domain, then there is a greatest common divisor of this. Okay. So in a UFD, you can define. How will you define a GC? Suppose this is like you have been given such. Suppose you have been given such factorizations. So you define GCD A comma B by P1, or maybe you can take just P1 to the power PM to the power SM, and here I should write SI or RI can be 0. Okay. So if something is not in the expression, we put 0 in the power. So this is like minimum mean R1 S1 times the power mean RMSM, and you can show that this actually will satisfy the criteria for the GCD. Okay. Okay, that's it for today. Because I don't want to go much further, because from the next class, I mean the other professor, he will actually be taking over. Okay, so that's it. See, he's a brilliant teacher.